Hello everybody, I'm Francesco Leoni and I'm a PhD candidate at the Norwegian University of Science and Technology in Trondheim. Today I'm going to present you a work on the behavior of an aluminum alloy wire under different temperature conditions. Recently, analysis of the behavior of a new solid-state joining process known as the hybrid metal extrusion and bonding process has been carried out. Until now, the development has been done using a combination of a 3D computer-aided design, rapid prototyping and laboratory testing in accordance to well-established design methodology. The high bond method utilizes continuous extrusion as a technique to enable filler material additions. This metal addition is done by feeding a filler wire with a diameter of 1.4 mm into the specially designed high bond pinpoint extruder as shown here in the figure. The wire feeding in the process is a crucial part of the wall joining operation. In a previous work by the authors, the special software package Deform 3D has been successfully employed in modeling the material flow pattern inside the high-bond pinpoint extruder using the default flow stress data provided by the software material library. But now, to upgrade the material properties used as input to the simulations, a series of dedicated tensile test experiments have been carried out in steps from room temperature and up to 500 degrees Celsius, employing the 1.4 mm diameters aluminum alloy 6082 wire. This covers the entire temperature range, being typical of the extrusion process. The measured engineering stress strain curves serve as a basis for the analysis, and in addition, selected fracture surfaces have been analyzed using a scanning electron microscopy to reveal the fracture mechanism. The chemical composition is shown in table here, and the wire appearance is shown in the two figures. The manufacturing route of the tested wire is here presented. The homogenizing of the 95 mm diameter direct cast extrusion billet was carried out at a heating rate of 200 degrees Celsius per hour. The extrusion billet was then held at 540 degrees for 2 hours and 15 minutes and subsequently cooled down to room temperature at a cooling rate of 300 degrees per hour. Prior to extrusion, the billet were preheated at a heating rate of 100 degrees Celsius per minute up to 500 degrees Celsius. The preheated billets were then hot extruded to blank wire of a target diameter of 2.7 mm at a ram speed of 0.6 mm per second. Following extrusion, the blank wire was first shaved and then cold drawn in steps down to the final diameter of 1.4 mm. In the cold drawn condition, the wire displays a Vickers hardness of about 130, and besides some minor surface imperfections, the wire surface appeared smooth and contained no cracks. Tensile testing was carried out in steps from room temperature to 500 degrees at a constant strain rate of 0.0011 per second, using an Instron 5985 testing machine equipped with a special heating chamber and special grippers that made testing of the thin wire possible. The measured engineering stress strain curves at different temperatures are shown here in figure. As expected, the softening of the aluminum alloy starts already at very low temperatures. The strength then continues to drop with increasing temperatures. At 500 degrees, the UTS is as low as 24 megapascal. In contrast, the fracture strain shows a different temperature response. Up to 200 degrees Celsius, the fracture strain appears to be essentially unaffected by an increase in the testing temperature. However, at 350 degrees, the material starts to behave more ductile before it becomes brittle again at temperature of 500 degrees Celsius. From measured curves, the data presented for the fracture strain and the ultimate tensile strength (UTS) have been extracted. In these two figures, it is possible to see the trend of the two parameters with respect to temperature. True stress to strain curves at each temperature can be calculated. These curves, which show how the plastic flow varies with the accumulated plastic strain at different temperatures, can be described by the equation shown, where N and K are the strain hardening coefficient and the strength coefficient respectively. The table here presented summarizes the values of N and K being obtained following the fitting of the equation to the experimental true stress true strain data. Figure here presented shows selected fracture surfaces of tensile specimens tested at different temperatures. Necking in combination with considerable dimple formation are observed at all four temperatures, indicating that the tensile ductility of the aluminum alloy 6082 filler wire is satisfactory. Moreover, a closer inspection of figure reveals that the tendency to necking and dimple formation becomes more pronounced with increasing temperatures. But when the temperature is raised to 500 degrees Celsius, the fracture mode becomes completely different, as shown here in figure. This indicates a change in the failure mechanism. At this temperature, necking is no longer noticeable. Figure B shows a lateral view of the same fracture surface. It appears rough, probably because intergranular slip and grain boundary sliding become predominant at high temperatures, which, in turn, promote separation between grain boundaries when the material is subjected to tensile stress. This type of failure, being associated with negligible necking and intergranular slip, is typical of creep rupture. The following conclusion can be drawn from the investigation that has been carried out. At room temperature, the tensile strength of the filler wire is very high. At the same time, as the ductility is correspondingly low, and this is due to the fact that the wire has been cold drawn down to its final diameter of 1.4 mm prior to the tensile testing. The tensile strength of the filler wire decreases with increasing temperature. The softening starts already at a very low temperature and the strength continues to drop within the entire range examined. Necking, in combination with considerable dimple formation across the fracture surface, are observed at all temperatures up to 350 degrees Celsius. This shows that the tensile ductility of the aluminum alloy 6082 filler wire is satisfactory. The tendency to necking and dimple formation becomes more pronounced with increasing temperature. But when the temperature is raised to 500 degrees, the fracture mode becomes completely different and indicates a change in the failure mechanism. No necking is visible and the fracture surface appears rough. This type of failure, as said before, is typical of creep rupture. All these results will be used for a more realistic finite element simulation of the I-bond process. Further developments will see the study of tensile behavior under different strain rate conditions. to further upgrade the model implemented. Thank you for your attention.